How's work?
Good.
Good?
Yeah. Good.
All right.
Why not?
So I have a few announcements for you guys. As you know, we have a midterm on Thursday. So it's going to cover until this lecture. So we're going to have determinant, indeterminate structure. There definitely will be a question on the determine the degree of indeterminacy, kinematic, and static. And I'm going to ask you to show the redundant and the degrees of freedom. Another question on cables and arches. There'll definitely be either a cable or an arch, so try to prepare well. And I believe the third question is going to be on the virtual work. The third question is going to be on the conjugate beam or the double integration method. So one of them is going to be in the exam. And a fourth question on the concept of real work or virtual work. So we are going to have 4 questions. 100 points, I believe, is going to be 25. So try to study the 4 topics very well. So that's for the midterm. Does anybody have any question?
Yeah, wasn't the midterm for the 2nd of October?
Yeah, it's gonna be Thursday next week. But is it holiday or is there school on the 2nd of October, right?
Yeah.
If I use working, okay. All right, that's for the midterm. So the second announcement that I have, so when I taught this class in 2022, I taught all the theoretical stuff at first, and then we started the SAP 2000, the ETAPS, and the project at the end of the semester. So the student complained that they didn't have much time to finish the project, or they were having a limited time. They finished and they did great, but the thing is they thought that it could have been better if they started a little bit early. So in the years after, I started the project and the SAP 2000, all this stuff in the middle of the semester. So I cut the theoretical stuff a little bit and then started explaining ETAPS and SAP and tall buildings. So because I know there's a lot of mass and a lot of dynamics and statics and a lot of stuff going on here. So we cut this stuff with something a little bit exciting. So, and then after we finish, you are gonna have more time to work on your project while we keep progressing in the theoretical stuff. So I believe today is gonna be the end of all the theoretical methods, and then we are gonna use the analysis, the structure analysis using software from next week, and or maybe the week after the midterm. It depends on how we are gonna progress today. And then you are gonna have at least 3 weeks or 1 month before the end of the semester that you can work in parallel on the course project and also on the theoretical stuff that we're going to explain in the last months. And then by the end of the semester, in the last lecture, we're going to have our last midterm, the second midterm. How about that? Does that sound good?
Yeah.
Yeah.
For the programs, we'll have like a student license.
Well, I tried with the university. I believe right now they have the SAP 2000 and the ETAPS on the Citrix platform, so they have a lot of licenses there. But I tried Citrix many times. It's very slow and it's slower than the normal ones. So what I did with my students in the last few years, we downloaded the trials one. We only need SAP 2000 in the first month, like I believe in 2 weeks or something. And we're not gonna do the project in SAP 2000. We're gonna do it on ETAPS. So don't start installing ETAPS on your computer unless you are ready to solve or already ready, because so that you don't use the 1 month license, because some students will install it now and start the 1 month from now, and when it comes to do the homework, the license is gone. So that's what I did. So once you are ready to do the SAP 2000 and install the software and take advantage from the 1 month license, and then once you finish it, you install ETAPS, and we are going to take advantage from the 1 month license. So but by the end of the semester, we are going to be covered because we only have October and November. That's it. So we need SAP 2000 in October and ETAPS by the end of October and mid-November. Does that sound good? All right. So let's continue the topic of virtual work that we started last time. All what I need from last time is the rule. Okay, let's right here. Virtual work. If you guys remember last time, we came to the conclusion. I drew like 3 systems. One of them is the real system, one of them is the virtual system, and we drew a third system where we were able to combine the virtual with the real system so that we can find a relationship between the virtual load and the real load. And we came to this conclusion that the Q multiplied by delta B is going to be equal to the summation of FQ multiplied by FBL over EA. That is the main equation from what we did last time. I spent at least an hour to prove this one. So Q is the load that comes from the virtual system. Delta is the deformation from the real system. FQ is the internal forces in the virtual system, and this is actually, if you remember, this was the delta LB that comes from the real system, but we were able to find, use the stress-strain relationship to find this part. Okay, so it was something like this. Let's say that is what we did last time, something like this, and we had a roller. That is our B system. B system is the real system, and that is the second system. That is the Q system. We usually put, like, let's say I have load B here and load Q here, and usually we put Q equal to 1. I never put Q any number other than 1. We usually put it 1 because this is, and we call it unit load. But this rule applies for any Q. If you put it 10, you can put it 10, 100, whatever, but 1 is the easiest one. So what we are saying is, let's put the deformation. This is the real system that we want to solve. This system, we don't want to solve it. It's a virtual system, but it's going to help us to solve for this deformation. So this load, once it's applied, is going to make a delta equal to delta B. And actually, I want to find what is the value of delta B. That is what I want to find out. When it's Q applied, it's going to make a delta, and this delta is going to be equal to delta Q. This one, I don't want to find it, but it's going to help me find this one. So we were able to prove from last time when I drew the strain energy and the work energy that the Q load that you put here multiplied by this displacement is equal to the internal forces in this system, the tension force in this, multiplied by the displacement of this member, delta LB. And then we were able to convert delta LB to this using the stress-strain energy. So that is the summary of what we did last time. But I know that you guys like steps. You like to solve problems step by step. You need to know when you have a problem, what you should do. So let's write the steps when you have a virtual work problem. First, number 1, find, solving virtual work problems. These are beams or trusses, okay? Let's put them step by step. Number 1, solve the system or find the internal forces for the main system. Like the truss that I gave to you last time, there was a truss like this. And we had a hinge here. And a hinge here. And we had a load 30 kilo-pound. Something like this. So the first thing that we did, we found the reaction and the internal forces for this main system. Okay, the question that I asked it last time, if you guys remember, you have this truss that I mentioned was, if you guys remember, I believe 16, 12, 16, okay. So I have 12 foot here and 16 foot here. All right, so I asked you last time that we need to solve this truss and we need to find what is the deformation at point P, X and Y. Definitely, I know that this truss is going to have some deformation, something like this. Once you push, this point is going to go X and is going to go Y. I want to find the deformation, delta X and delta Y. So, number 1, forget about what I'm asking for. Try to solve this truss. Find the reactions, find the internal forces. And we did this last time, and we found that the reaction, this is going to make a moment that way. So there should be a reaction going down, a reaction going up. And this is the one that is going to resist the 30. And we found that these reactions are 40 kips. 40 and 40. And then we found that this is going to have compression negative 40, and this is going to have tension positive 50. We did this all the last time, okay? So first, I need to find the internal forces. Forget what I'm asking for. Forget the deformation, forget anything. Find the internal forces, find the tension and find the compression. Number two, remove all loads from the original system. If this is a big truss and has multiple loads, take all the loads off. If it's a beam, take all the loads off, okay? And make this system cleared from loads. I'm gonna make this system here without any loads. Hinge and hinge. So if this system doesn't have any loads, what are the internal forces? 0, right? Okay, so the third step, apply, by the way, these steps is not here, so better you write it in your notes. Apply unit load at the deformation of interest. Okay, so the thing is, this is the free system. But the thing is, I'm gonna apply a unit load at the deformation of interest. Okay, so when I'm asking this question, find delta x and find delta y. So I'm asking you to find two deformation. So you have to draw this 2 times. So I have to have this, let me make it then 2. I'm gonna make a small one here. And another one here. Since I asked it for 2 deformations, so you have to draw this 2 times. If I ask for delta x at point B, so you apply a unit load at point B, and you will put 1 kips like this. If I ask you for deformation in y, you apply unit load in the direction of y unit kips. Okay, so you remove the load, draw the structure, and apply a unit load at the deformation of interest. You will ask me a question, hey, I don't know what is the direction that I should apply this load at, right? So you'll tell me, okay, what if I apply this load the other direction? It's fine. Apply it that way or that way, it's fine. At the end of the day, if you got the deformation equal to a negative number, that means that your assumed direction is not right. So it's in the opposite direction. So let's say I applied that direction and I found that the deformation is negative 1 inch. That means this structure is gonna move negative 1 inch that way, not that way. So either direction is fine, okay? So we applied the unit load. Once we apply, number 4, apply the work energy principle for each system separately. This equation, Q delta B multiplied, so you are going to apply Q delta B equal to the summation of FQ FBL over EA for each system separately. How I apply this equation? Okay, this is the B system, and this is the Q system. All right? Look at this. Q is always equal to 1. We agreed to this. So basically, I can remove Q. Delta B, but I removed Q based that we had an internal agreement that Q is going to always be 1. If you're going to change it different than 1, there's definitely Q here. So delta B, which is delta X that I'm looking at right now, is going to be equal to the internal forces from the Q system multiplied by the internal forces from the B system multiplied by the length of the member over EA. Most of the time EA is constant, so I can keep it for all the members. And this is summation because you have to do it member by member. You have to do this member first, multiplied by this member, and then this member multiplied by this member. So you take them one by one, and I told you that you can build a table, and once you build this table, everything is gonna be organized. Okay? Do you guys understand this? Clear? Okay. So what we did last time was a little bit easy. So let's make it actually a little bit difficult. Okay?
Professor, So when you say apply unit load at the deformation of interest, so like if we want to find the deformation at like the midspan of that vertical member,
Since this
can
is
we
a
do that?
truss, you cannot apply load in the middle. But let's say it's a beam.
Yeah.
The thing is, if you apply load in the middle here, that means this is gonna have a bending moment. So if a truss member has a bending moment, it's not a truss anymore, it's a beam. But let's say it's a beam. Let's say that this is a frame, and I ask you to determine the deformation here, you apply the unit deformation. Okay? All right, if I ask you here, apply the unit deformation and going Y, so you apply unit Y here. So any point that I ask for a unit deformation, locate this point and put a unit load and determine how's the internal forces in the older structure look like, and draw the normal force diagram or find the normal force in each member. And we're gonna do this for beams in a little bit.
What if you were to put the unit load for the Y deformation like going upwards?
Yeah, it's gonna be the same thing. All right, from my perspective, this point is gonna go down. So what you are gonna get the same exact deformation, but it's a negative number. So all what you have to do, you said that the deformation of Y is equal to 1 inch and it's in the opposite direction. Or you make an arrow and you show that this deformation is going down rather than going up. So for me, like sometimes it's a tricky. It's a big truss, sometimes you don't know. So I assume the direction, and once it's getting negative, that means it's in the opposite direction. All right? Okay, so let's make this a little bit difficult. What if I told you this structure doesn't have any loads? Because I told you here in step number 2, remove all loads from the original system. What if your structure doesn't have any loads, but it has settlement? Same structure, let's say this and this. Same dimension, 12 foot and 16 foot. And I told you this structure doesn't have any load, but it has settlement at the left support. This settlement is, this support moved 0.2 inch in the X direction and 0.6 inch in the Y direction. Basically, this support came here. So if this support came here, I would imagine that the deformation that is going to happen to this truss is going to be something like this. Somehow the foundation, the soil is loose, and then the support shifted a little bit, so it takes the whole truss that way. So there is no loads, but there is a foundation settlement at the left support. So let's see how we can handle this. We're going to apply the same rule. So, but look at the question. I ask you, find, let's say this is point B. Find delta X at B. Same principle. Remove all the loads. So this system is going to be the same. There is no load. It's going to be something like this, something like this. That's the original system, B system. And then I'm gonna put a unit load at the deformation of interest.
And
So
we can't find the internal forces because there's no load.
yeah, I'm gonna put them like, yeah, okay, I'm putting them now. 0 and 0, right? There's no internal forces coming from external loads. All right, how about I'm looking for the deformation X at B, so I put unit load at B in the direction of X. So I'm gonna put 1 kit that way on this system. This is the Q system. All right, let's find the internal forces here. If this is 1, I believe I'm gonna have a 1 reaction here, and definitely this is gonna make a moment that way. So I need a force to balance this, and it needs to make a moment of 16, so it's gonna be 16 over 12. If you find 16 over 12, it's gonna give you 4 over 3. So this is gonna be 4 over 3, and this is gonna be 4 over 3. And this is going to be negative 4 over 3 normal force inside this member, and this is positive 5 over 3 inside this member. You have to find these reactions by yourself. Okay, so let's find out how we can solve this problem. All right, I'm going to put the same rule, this rule, that Q multiplied by delta B equal to the summation of FQ multiplied by FBL over EA. All right, so we noticed something a few seconds ago, that this system doesn't have any external loads. So the internal forces FB in all members are equal to 0, right? So definitely FB equal to 0. So this whole thing is equal to 0. So Q multiplied by delta B is equal to 0. But the thing is, Q multiplied by B is not right now a single force. It's multi-forces. Why? Look at this. The thing is, let's see all the deformation. By the way, this rule applies for all the deformations in the structure, all the movement, all the external movement. This point B moved that way, right? And this point moved that way, and this point moved that way. So you multiply all the forces from the Q system by all the displacement in the original system. So what happened here, you are gonna multiply 1 by delta X that happened here. So we have delta X here, let's say this, plus the reaction 1 multiplied by 0.2, plus the reaction 4/3 multiplied by 0.6. And if there is a displacement here, you are gonna multiply by this force 2. So the work done on this system is all the forces from the virtual system multiplied by all the displacement in the original system. Okay? Let's say in this problem, when we solved it last time, if I told you there is a 30 kips applies on the structure and there is a settlement at the support at the same time, so you are gonna have all the things here that coming from the settlement and coming from this force, and then you are gonna have all the internal forces that coming from here. Okay? You guys understand that?
Yep.
So you are gonna superposition the settlement with the load. All right, so let's find out. So I'm trying to find delta X. By the way, I assume that 1 kips is going that way, so I don't know what is the direction of delta X. So I'm gonna multiply 1 by delta X. Then I have a reaction 4/3. By the way, I don't know what is the direction of delta X, so I'm gonna remove this for now. But I know what is the direction of 0.2 because it's given to me. And I have 1 is going that way. If they both are in the same direction, so their sign are positive. So I multiply 1, the force from the Q system, by the displacement. So it's gonna be 1 multiplied by 0.2. Why? Because the direction of the load and the direction of the displacement are in the same direction. And 4/3 multiplied by 0.6. So all this is equal to 0. So delta X is going to be equal to, once you solve this, equal to -1 inch. And that makes sense. Why? Because I knew if this support had a settlement in that direction, so definitely the delta moved that direction. But I assume the load is going this direction. So that means it's going to be in the opposite direction of the assumed load. Okay? All right. So I'm going to close this part for now. I also added another example. What if I'm trying to find the rotation, this here theta. So here I showed how to do it. I'm not gonna ask about it in the exam, but it's better that you know how to find theta. Like if you wanna find theta, I apply a unit load 1 ton meter or 1 kips foot and try to find, like here, try to find the Q system and integrate the same way. The Q system was the B system, all right? But I'm gonna leave it for now because we need to start the beams.
Could you please explain again the classification?
Just this one?
Yeah.
All right, so the thing is here, I'm gonna use the same rule, that the summation of Q, the Q multiplied by delta B is equal to this. The system, the main system doesn't have an external load. However, settlement is considered as a load, but it's an external deformation. Like sometimes the structure generate internal forces from the settlement, okay? So once there's no loads to remove and there's no loads on the original system, so I put the B system like this, so all the internal forces are 0. So FB is equal to 0 for all members, so that side is equal to 0. So I have the left side. The left-hand side is usually devoted for forces multiplied by displacement. Forces from the virtual system multiplied by the displacement that I'm looking for in the original system. So I know that this is delta X because I'm looking for delta X, right? So I put 1 kips here. It's gonna be multiplied by the delta X that happened here, but we still have external displacement here already there. And I know them, I know their values. So I multiply the reactions here by this and the reaction here by this, because that's a work concept. All the external forces multiplied by the deformation that they make. So you already have some forces here and some deformation here, so this already exerted a work. You know when they will not exert work? When this point doesn't move, because the force multiplied by zero displacement is going to be equal to zero work. Okay? All right, so we right now can close the topic of thrust and we can start a new one and talk about how we can apply the concept of virtual work in beams.
May I ask you one more question?
Yeah, sure.
Why we multiply by 1 times 0.2? Because both are horizontal.
1
Yes.
is the force multiplied by the displacement in the same direction of the force. So I have 1 multiplied by 0.2, because the 1 is the one in the same direction of 0.2, and 4/3 multiplied in the same direction of 0.6. So we multiply the force by the direction of each displacement. And if I ask you, try to find the deformation delta y, like if I want to find out how this went down, what would be the difference in the problem?
Just the one kid is
Exactly, excellent. So all what I'm gonna do, I'm gonna remove this whole thing. I'm gonna put unit load that goes down. And let's do it. It's gonna be something like this. And let's put 1 kips going down. 1 kips going down is gonna make -1 in this member, and this member is gonna be, I believe, 0. This one is gonna take it. Oh, so there's no reactions here. So basically, it's not gonna give you like, this one is, well, actually we need to solve it. Like, okay, if this one, yeah, this one is gonna have 1 kips, and this one is gonna be -1, and you're gonna solve it that way. So these two is gonna multiply by, like, it's gonna be 0 multiplied by 0.2 and 0 multiplied by 0.6. Okay? All right, so does anybody have any questions?
So there's vertical displacement would be 0.
Let's see. There's definitely vertical displacement. All right, so you're gonna have here 1 multiplied by delta y plus 0 thing is, this thing is indeterminate. So when you apply this load here, and you take a section here, that's why I was saying I'm not sure if this is the right answer, because if I'm taking a section around this joint, this one is going to give you a force here, and this one is going to give you a force here. So they both are going to resist it. So that's why I was saying I'm not sure about the reactions. We need to solve it. Maybe we will solve it with SAP 2000 next time. This one was easy. Like when I put a unit load here, I know that this one is the one that is going to take the reactions. But this one, if this point went down, because if we think about it about deformation wise, if this point went down, this one is going to went down as well, and it's going to develop a compression force in both. So that's why I'm not sure if the reactions here is going to be exactly 0. So maybe I will double check on that. The best way to do it, because this is an indeterminate one, so it's still with SAP 2000. Or we use it one of the methods that we learned. I'm not sure if we didn't do it yet. There's a method, it's called the consistent redundant. We make this roller and we try to find the missing reaction. So maybe we do it with SAP 2000 and see if these reactions are equal to 0 or not. Okay? All right, but I'm sure there's a Y reaction here, a Y deformation here. It's not equal to 0. Okay, so let's now move to beams. So trusses actually is the easiest members to find the deformation for using the virtual work method. Why? Because the thing is, the normal force doesn't change over the cross section. The normal force is constant. It is always equal to one number. It doesn't change. But the thing is, with beams, we have a problem. That the bending moment or the internal force or the shear force keep it changing over the cross section. And I proved it to you, I don't know, like 2 lectures ago, how this is changing. And right now we need to move from the summation to the integration, right? Okay, so let's actually put what we virtual work for beams. This is our beam. And let's say this beam has a load B. And once you put the load B, the deformation is going to be something like this. So that is the B system, the main system, okay? Same concept apply. Do you remember these steps? Find the internal forces in the main system, remove all the loads, apply a unit load at the deformation of interest. Let's say that we are interested in the deformation at this point. So the deformation at this point is this. This is our delta B. That is the deformation that I'm interested at. So if you are interested in this deformation, take the B system, remove all the load from the B system, and then put a unit load Q. This Q can be equal to 1 at this point, and try to find the deformation of this system. So the deformation is going to be equal, it's going to be something like this once you put this load. And the deformation here is going to be equal to delta Q. And the thing is, where's the rules here? I want to find the best way to do it for you. Okay, let's put this rule. Okay, I'm gonna put Q multiplied by delta B is equal to the summation of FQ multiplied by FB over multiplied by L over EA. That is the one that worked for trusses, and the summation sign was there because I have multiple members and I want to do it for all these members. This rule cannot work for the moment. Why? First, the thing is, the internal forces is keep it changing across the member. Like the moment here is 1, 2, 3, 4, keep changing. That's number 1. Number 2, right now the forces are not normal. The forces are moment. So we're gonna have similar rule. This rule is equal to Q multiplied by delta B equal to the integration. I converted the summation into integration because this function is variable, is not constant. So I need to integrate over the length of the beam from 0 to L. And since I don't have normal force anymore, I have moment, so this is gonna be MQ. And this is gonna be MB multiplied by L over EA is gonna be converted to EI because the moment is about the EI, not the EA. That's the moment stiffness of the beam. So this is the main rule. You will find here how did I prove it. So basically, I did it, I believe, last time. If you guys remember, we had from before d square y dx square equal to m over EI, and this is equal to d theta dx. So basically, d theta is equal to m over EI dx, and then we were able to say that if we want to find a du, which is an infinitesimal strain energy is equal to m d theta, because I have moment, and the moment at any cross section, like let's say the moment here, mb, I want to find the moment at this point. So the moment at this point is mb. I want to find the theta that happens between the difference between these two cross sections. Here it has theta 1, here it has theta 2. So the difference is d theta. So m multiplied by d theta equal to the strain energy is stored in this infinitesimal distance. Do you guys remember that? And then I have the strain energy. If you want the total, you integrate du over the length of the beam from 0 to L. So you integrate this from 0 to L m d theta. Okay? And by the way, this m is coming from the Q system, and this is mq, and this is going to be 0 to L mq, and d theta is coming from the B system, and d theta b is equal to mb, so you're going to have mb over ei dl. We did this last time, if you guys remember. Like q delta b, that is the strain energy. We have mq theta b, but it's d theta, and then we integrate the whole part. And this is going to be something like this. That is the rule that we have for this beam. All right, so the problem is mq and mb. Like this is the B system, and this is the Q system. So you want to tell me that if I want to find the displacement at this point, I'm going to put a unit load 1, and then I'm going to find the bending moment diagram. So let's actually put the main system here. And I have B like this. When you put B like this, you're going to end up with bending moment positive like this. This is MB, the moment of the main system. If you want to find the deformation, at this point, you are going to put Q equal to 1, and you are going to have a bending moment like this, and this is MQ. So you want to tell me that you want me to find the function of MB and put it as a function of X here, and the function of MQ and put it here as a function of X, and integrate all these functions? Yes, I want you to do that. It's going to be difficult, but we are going to find a way to make it a little bit better. All right? So we need to find.
Giving us easy beams.
What was that?
Giving us easy beams.
No, the problem is in the integration. The integration is two functions. There's a table that we are going to use. Well, definitely it has to be an easy beam, but even with an easy beam, it's going to be difficult. I'm going to solve right now the simple beam, and we are going to have a lot of like 3 lines of integration just for a simple beam. So if it's a continuous beam, there's no way that you can do it. But we need even to reduce this all integrations, because definitely you are going to make an error while summing all these mathematical terms together. So we need to find a way to avoid that. All right, but we need to solve it that way so that we can appreciate the simple procedures, okay? All right, so I believe I was trying here to show you how did I came up with this rule. But I used, if you guys remember from a couple lectures ago, I tried to find U for a beam and tried to find the work for the beam, and we equate them together, and we were able to come with something like this. But the thing is, what if I ask you not to find the deformation? I ask you to find theta. Like let's say I asked you to find theta here at this point. Theta, that means the slope of the beam at this point. So same concept. You are gonna make another system, another Q system, but rather than having a unit load Q, you are gonna have a unit moment here. M Q equal to 1, and then draw the bending moment diagram of this moment. So this bending moment diagram is gonna be something like this. All right. If I ask you to find a bending moment diagram at the end of the beam, like here, so you are going to have a bending moment something like this. So that is the bending moment diagram. Depends on where the theta is. And the rule, this is for deformation delta B. So, and the rule is going to be equal to the MQ, the concentrated load, which is equal to 1, multiplied by theta at the point of interest, is going to be the integration of the same thing, MQ MBL over EI. So the difference is MEQ right now is equal to 1. Theta B is the theta that I want to find out at this point. This one, theta B. And you are going to integrate the moment from MEQ with the original moment. Or this one with this one, depends on the location of theta. Do you guys get it? Same concept. Number 1, find the internal forces for the main beam. This is the main beam, has a concentrated load. I got the main internal forces, which is the bending moment. And second step, remove all the loads. I removed all the loads. Third steps, I apply unit load at the deformation of interest. If the deformation of interest is delta, so I applied unit force. If the deformation of interest is theta, I apply a unit moment. If this theta here, I apply unit moment here. If at the support, I apply unit moment at the support. Get the bending moment diagram. I forgot here to write, but you guys definitely got it implicitly. Get the bending moment diagram or the normal force diagram for the Q system and the B system. Once you have them both, you can now solve this for this step. All right, so let's do this for simple beam and see. I wrote here a note. I said both shear and moment contribute to the beam deformation. Okay, so but right now I only showed the moment. I didn't talk about shear. Do you guys remember why? Because I said something last time about the shear deformation. Shear deformation, the amount of shear deformation that happens in beams is very, very minimal. So I said both shear and moment contribute to the beam deformation. However, the shear deformation is typically less than 1% of the flexural deformation that comes from the moment. The shear deformation is high when you have a really deep beam. Like if you have a deep beam, in the tall buildings, we're going to have something called outriggers, or there's something in tall buildings is called transfer stories. Maybe we talk for 2 minutes about this. Sometimes the shear deformation is important. If you have been to any tall building, look at this. You go to the building, like from the inside in the first story, you will find holes, like there's no columns in the middle. You can see an open space of 100 foot without any columns. Because that's the reception of the whole building. That is actually the sign of the building. You need to make it very fancy, no columns, open space, all that. And then once you go to the upper stories, you will find apartment with small spaces. So what we do is we make a transfer story between the first floor and the rest of the building. And this transfer story, let me write it here. This is my tall building. Something like this, and there's a lot of columns. The thing is, in the first story, we come like this and we remove a lot of these columns so that we can make open spaces for the reception. Even the height of the floor is much higher, maybe double a story or something. And then we do one of two things. We either make transfer beams. The thing is, I don't want these 2 columns and I only need 1. And maybe this, I escape 1 or escape 2 and make this. And I only have this amount of columns. Okay, that's totally fine. But how about these columns? What we are gonna do? How they are gonna transfer the load? We need to find a way to transfer this load to somewhere else. Other than that, the whole building is gonna collapse. So we make a transfer beam here, a very deep beam in this story. And sometimes this beam is the whole story height. You see this height is a reinforced concrete, heavily reinforcement. Maybe you can find 10 layers of reinforcement. 1, 2, 3, 4, 5. Because that's not a column holding 100 story or maybe a 50 story. So there's a lot of load coming on this beam. And sometimes if these columns are huge and there's many of them, transfer beam is not enough. We make a whole transfer slab. Like the whole thickness of the slab sometimes reach 2 meters. And it can take the whole story. And this story is not usable. It's just a transfer story, okay? But most of the time we try to make a transfer beams. Like if you look at the plan of this building, like if I'm looking up there, you'll find out that there is a transfer column. So I make a wall here, and this wall is something like this, and this wall has a column here. This wall is supported on two columns from here and here, and there's a bunch of columns supported on it. And sometimes you have a column here, so you make another transfer slab like this, and this the transfer beam, something like this. And you'll find this story, nobody can access this story. It's a bunch of walls hitting each other. And they use this for storage, they put the chillers for the AC, they make it as a services story. Okay? So why here there's shear deformation? Because it's something like this. I have a deep beam and have a column here, and this column coming with a huge shear on this wall. That's why I make this beam is huge, because there's a lot of shear. So if the shear load is big, definitely the shear deformation is gonna be high. So that's, I believe, one of the cases when we have really huge shear deformation, just for your information. It's not always 1%. Okay, let's get back to business.
Example using virtual work.
Compute the deflection and slope midspan of a simple beam. Compute the deflection and slope for this simple beam. It has a load W. We did this with the double integration method, you guys remember? And it has a length L. And I ask you find the slope midspan, find the deflection midspan and the slope at the support. And the slope here. Why didn't I find the slope here? Because the slope here is 0, right?
Yeah.
It's gonna be something like this, and it's gonna be 0. All right, so let's see how we can solve this problem. Our rule is here. This is our golden rule. This one. We wanna find the deflection, delta V. We're gonna use this. But the thing is, to use this, I wanna find what is the MEQ and what is the MP. I know that B is the original system, and I know that Q is the virtual system. Okay, find the internal forces for the main system. That's a very easy system to find the internal force to. So I'm gonna write this system, something like this. What is the bending moment diagram on this system? It's gonna be a parabolic curve, and this parabolic curve is having in the middle WL squared over 8, right? This is the MP of the system. And then the Q system, I told you, remove all the loads from the original system. So I will come to this system, and I will remove all the original loads. I remove all the distributed loads. Here, this one is under distributed loads. This one doesn't have a distributed load. All right, that's the virtual system. Apply unit load at the deformation of interest. I ask you to determine the deflection at the midspan. So midspan is here. I apply unit load. This unit load Q is equal to 1. Draw the bending moment diagram for this system, the Q system. This is MQ. So do you guys remember the bending moment diagram if you have concentrated load in the middle? It's gonna be something like this. And the moment here is BL over 4. B is 1, and you have L, so 1 multiplied by L over 4. Here, the reaction is WL over 2, WL over 2. Here, the reaction is 1 over 2, and 1 over 2. All right, I got the MEQ, I got the MB. I'm ready to integrate these two shapes together. If I find the function of the moment in X and the function of this in X, integrate them together is going to be a very simple solution. How can we find that? Same thing like we did for double integration. We take a section here and we try to find a general equation for the moment. So I can find the general equation of the moment here. I can say that the moment for the original system at any distance x is going to be equal to WL/2 multiplied by x minus the distributed load multiplied by x multiplied by x/2, so it's going to be WX²/2. Do we all agree on this? Take a section here, get the moment. It's going to be this load multiplied by x, and then the distributed load multiplied by x/2. Okay. That's an easy one. How about MEQ? MEQ is a little bit tricky. Why? Because it's the two lines. This line goes down and this line goes up. The moment before this point has an equation, and after this point has an equation. So I would say for x less than L/2, the moment is going to be equal to MQ at distance x is going to be equal until here. It's going to be equal to 1/2 multiplied by x. Like if I'm going to get it to at a it's going to be equal to x/2. If the x is more than L/2, so MQX is going to be equal to, if I want to take it here, it's going to be the same thing. It's going to be x/2 minus this load. Like let's say I'm taking the moment here, so it's going to be x, it's going to be 1/2 multiplied by x minus 1 multiplied by x minus L/2. You guys understand that? Here, and I have this load here, 1. So if I'm taking the moment here, it's going to be equal to the 1/2 multiplied by x minus 1 multiplied by this distance. This distance is equal to x minus L/2, because this is the whole distance. This is x, and this distance is L/2. Do you guys got that?
Yes.
Okay. All right. So what I'm gonna do now. I'm gonna apply the integration equation, which is over there. So I'm gonna say that Q multiplied by delta be equal to the integration from 0 to L MQ MB L over EI. So Q is equal to 1, and I'm only interested in delta B. And the thing is, my integration right now is not continuous. It's broken here. So I have to divide the integration into two zones, from 0 to L/2 and from L/2 to L, because I have two equations for Q. So I'm gonna make this the integration from 0 to L/2. MQ in this zone is equal to x/2. It's gonna be multiplied by well, I'm gonna do something. This is right, but I'm gonna make it easy just to calculate MQ, MBL, and I'm trying to find 0L, MQ, MBL, that's it. Once I found it, I can divide by EI and I can do this part. Or I can do the same way that I'm doing, but I wanna find just the part that is variable. This is not L, this is dx, and this one should be dx. Because here I had this one is d theta, and this one's supposed to be dl, and it depends on the distance if it's dx.
Yeah, dx over
Okay. Okay, so it's supposed to be dl or dx, so I'm gonna leave it dx. Once I integrate, it's gonna be l. dx. Okay, so this one is gonna be into two zones, from 0 to L/2, and another zone plus from L/2 to L. Let's find this integration. So this integration is going to be MEQ equal to x/2 multiplied by MBX, which is WL over 2 multiplied by x minus WX squared over 2, and I'm gonna have dx here. And then the second part is gonna be equal to MQ is equal to x over 2 minus x minus L over 2. And all this is multiplied by WL over 2x minus WX squared over 2. And all this is dx. That sounds like a long integration. I'm not gonna do it, but I did it here. All you have to do, you have to expand all these terms. This part, you're gonna do it separately from this part because this has a different integration boundary. You cannot group any of these terms with these terms. So you're gonna multiply this with this, is gonna give you an x squared thing. And you multiply with this, is gonna give you an x cubed thing. And it's gonna end up with 2 terms. This is gonna multiply this with that, and this was that, this was this, and this was this. So you're gonna find how did I expand it here. I'm not gonna do it because it's gonna take like 10 or 15 minutes. But at the end of the day, once you do this integration, you're gonna find out that this integration is equal to 5WL to the power 4 over 384. Okay? But this is not the solution. This is just the part that has integration. I take AI is constant and I was just calculating this part. So I know that Q is equal to 1 because I put unit load is equal to 1. So I can say that delta B is equal to 5WL to the power 4 over 384 EI. All right, that's the solution. Do I want you to do this in the exam? No. If you want, it's your choice. Let's see how we can solve this problem in the exam. I don't want you to do all these variable multiplication. Let's see what is the easy way to do this. By the way, I say right now, don't do it in the exam, and there's people who's gonna do it in the exam. Don't know why. All the years, I say it's gonna consume your time, and I don't account for this time in the exam. It's gonna take 15 minutes from the problem. Even that you can do it in one line using what I'm gonna tell you right now. So focus on this part and forget this part. Forget this integration part. Okay, there's a rule, or there's something called geometry integration. So if you have a geometry like this, a parabolic curve, and you wanna integrate it with another geometry like this, let's say that you have a function that you want to integrate from 0 to L, and this function is MQ, MB, L. We are going to name it different names because this is how it is in the textbook. So this is equal to 0L, M1, M3, DL. So this shows L, or DX, for both of them. All right. So the textbook is naming MQ M1 and MB is naming it M3, okay? The textbook is saying that this is gonna be here. This is gonna be equal to a factor C multiplied by M1 multiplied by M3 multiplied by the length of the beam. What does that mean? So basically, let's say that the shape of the bending moment that comes from MQ and MB is something like this. Let's say that this is MB, is a rectangle, something like that. MB. And the bending moment that comes from MQ is something like this, these two shapes. This is M3, the value here is M3, and the value here is M1. So let's say M1 is equal to 4, and M3 is equal to 8. So basically, you're gonna have a table, I'm gonna give it to you, something like this. Tells you if you are integrating a parabolic curve, parabola, with a triangle, go in this table at the parabola side and with the triangle side, and try to find the factor C. You're gonna find that the factor C here in this case is equal to 1/3 multiplied by the moment value here and the moment value here. So multiplied by 4 multiplied by L, multiplied by the length L here. And then you solve the whole integration problem. So in our case here, I have a parabola with this shape. By the way, this shape, two triangles, is different from one triangle. So you will come to the parabolic curve and try to find the two triangles. This is the two triangles together. And actually it's giving to you general. Like the point is not in the middle. Because sometimes I might ask you not to find the deformation here, find it at somewhere left or right. So it tells you if you want to find this value, is gonna be, okay, I'm gonna go here, is equal to 1, for our problem, is equal to 1 over 3 multiplied by M1 multiplied by M2 multiplied by L plus A B over L. What is AB? AB is giving you a triangle like this and telling you that this distance is A and this distance is B, right? Let's apply it in our case. 1 over 3. M1 is the MQ, okay, which is this value. The value here. So I have the value M1 is equal to 1 L over 4. So I have L over 4. And M2, sorry, this is M3, because that's what the textbook is naming it. M3 is the value, the maximum value here in the middle, which is WL squared over 8 multiplied by L plus A is equal to, in our case, this distance A,
L over 2.
L over 2, excellent. How about B?
L over 2.
L over 2, all this divided by L. So this is gonna be L squared over 4 over L. So I'm gonna cross L, 1L with another one. So we're gonna end up
L
with
over 4.
L over 4 plus L. It's gonna be 5L over 4. So once you finish this, you are gonna have, this is equal to 5WL to the power 4 over 384. Same thing that we had here. All right? So that's for this part. If you want to find the rotation at the lift support, same thing. But the only thing that is different, I want to find the rotation here. Let's put it on the other side of the board. All right, the only difference, if you want to find the rotation at the support, I'm gonna put a bending moment MQ equal to 1 here. And I'm assuming that the direction of the rotation is this direction. However, it's supposed to be in the other direction here. So let's put it in the other direction. Why? Because this beam is gonna bend that way. So this is rotating that way. It is always, if you know what is the positive side, try to put it the positive, put the unit in the positive direction. Okay? Can you guys draw the bending moment diagram for this? What is the moment here?
0.
0. And what is the moment here?
Maximum, like 1.
Which equal to 1, right? So it's gonna be something like this. 1, and this is a positive moment. Something like this. How about the reactions? Do you guys know what is the value of the reaction if you have 1 here? So you're gonna have a reaction here and a reaction here to counter this moment, and this reaction is gonna be 1 over L. 1 over L and 1 over L. Why? Because the thing is, if you take the moment here, you're gonna have 1, and this is 1 over L multiplied by L is gonna give you 1. So you do some Fx, some Fy, some of the moment, you are gonna get this answer. Okay, so that is the new moment that I have. So I'm gonna do the same integration. So the integration is gonna be equal to MQ theta be equal to the integration from 0 to L MQ MB dx over EI. So the integration of MQ MB dx from 0 to L is gonna be easy. I'm gonna go to the table. I'm gonna try to find a triangle that match this thing. So I have a triangle here, and I have a bending moment here. So it's gonna be 1 over 3 M1. M1 is equal to, M1 is the Q, which is equal to 1, multiplied by M2, which is WL squared over 8, multiplied by L. So when you do this, it's going to give you WL cube over 24. So MEQ is equal to 1, sorry, not 0, 1 because I put here, this is equal to 1. So theta B is going to be equal to WL cube over 24 multiplied by EI. You guys got that? Very easy, very simple, no integration. You just look at the geometry and try to make. And this table is really, really easy. Try to find MQ. Actually, it's here Q, but once you put it here, you put 1. So, because sometimes there's two moments. So, like if you have a trapezoid or something. So this is MQ and this is MB. And try to find the two shapes and use the factor C that matches your geometry. Okay, so I'm gonna do something really quick.
Professor, I have a question.
Yeah.
When the diagrams are filling up, why are you using the triangles if MP is like half a circle, a quarter of a circle? Like the diagram.
This one? Half a circle, like what? Not parabolic?
Yeah, like you're using the two triangles down there,
Uh-huh.
but I thought you're supposed to use MQ, like part of MQ. And
Oh, you mean like if this is not linear, if this is a curve or something? Because I don't understand what is half a circle.
NP is the half circle.
The thing is, usually the Q ones is not gonna be curved. It's always gonna be linear because you always put a unit load or a unit force. You don't put a distributed load. So it's always gonna be something linear or constant. But for the beam, you might have a distributed load. So the distributed load, you're gonna end up with having a parabolic curve. But you mean circle, you mean the shape of the geometry?
No, I don't mean the shape. I just mean orange using half of MB.
Oh, you mean like, what if I take half of this and integrate this part together? The thing is, it might make your problem difficult because the thing is, we don't have the geometry of half a parabolic curve. So because I thought about it, what if I take this triangle, one triangle, and integrate it with this? The thing is, I don't have a geometry for half a parabola here. So I have to take the whole parabola. Okay? All right. Well, I wanted to tell you the idea. What if I have a cantilever? How this is gonna change things. Like, let's say my problem is same problem like I have right now. I have a cantilever like this and have distributed load W over length L. Same concept. I have the MV system. Can you guys draw the bending moment diagram for this?
The same as that one.
But this is distributed. This is concentrated.
Oh, yeah.
And this is simple beam. So here's the moment that, yeah, it's parabolic curve. Basically, we make a dotted line like this, and then you drop a parabolic curve from here. And the drop here is always, you know what, I forgot actually the drop. W is square over 8, I guess. Yeah. If you measure this drop from this line, the line that goes from here until WL is square over 2, and make this parabola, this is how we draw it. Something like this. If you want to draw this parabolic curve to scale, we usually put a point where it's WL is square over 2 and make this 0, draw a straight line, and in the middle it goes down WL is square over 2, and then I make a parabolic curve. And I have this in the shapes here. I have this shape here, the one that has a negative parabola. Okay, so that's the main system. And I'm asking to find the deformation at the tip here. So at the tip, I'm gonna remove all the loads. I'm gonna put a Q load equal to 1 here. If you put a Q load equal to 1, you are gonna end up with a bending moment diagram, linear, 1 multiplied by L here. So this is negative and this is negative. By the way, when I integrate, if the bending moment diagram is positive in one of them, like let's say that you decided to make the cube goes up. So the bending moment diagram here is gonna be positive. So positive with negative is gonna end up with negative sign. If the two diagrams is negative, so we don't have to worry about the signs. M and Q and MB, negative, negative, positive. But if one of them is negative and one of them is positive, so the sign is gonna be negative. Okay, so right now I go to the geometry table. It's called table A2. I'm gonna give it to you on Canvas. It's called the values of the product integrals. And I have the MP is parabolic curve, and the other one is a triangle. So you will find out that the integration and I want to find the integration of MEQ B dx. So here's it's equal to 1 over 4 this value multiplied by this value multiplied by L. So it's going to be L multiplied by that L squared over 2 multiplied by L. So this is going to be equal to WL4 over 8. So Q is equal to 1. So delta B is equal to WL to the power 4 over 8 EI. So do you guys get that? That's, I recommend not doing integration, the one over there, the one that I did in a little bit, because it's gonna take a while and definitely you're gonna make a mistake. Even me, while solving it, I get like lost in the terms. You might miss a sign, you might miss something, and you're not gonna get there. So basically, draw the bending moment of both of them. One of them is gonna be parabola, and one of them is gonna be linear. And look at the geometry and see who matches who, and get the formula. All what we need to do, we know that we are gonna multiply this moment by this moment. That's for sure. But the only thing that it changes here is this factor. All of them is m multiplied by m, but one of them is half, one of them is 1 over 3, one of them is 1 over 6. We need to find what is the factor that we are gonna multiply here. So it's basically this moment multiplied by this moment, multiplied by L, and this factor is the one that it changes, okay? All right, so that's it for now. We covered the virtual work part, and I believe the homework is posted, and it's due next week. And next week we are gonna start a new topic, so hopefully it's gonna be more exciting than this topic.